Hey there, awesome physics students. Let's talk about what happens with waves whenever you have them trapped in a medium between two boundaries. Uh, at the boundaries, you're going to see a series of incident waves coming in, and then there's going to be some reflections at the boundaries. And then those reflections are going to interfere with the original waves. When you combine the original waves with the reflections, the result is standing waves. Unfortunately, I can't draw precisely enough to show you how it works, so we'll have to go to a computer. So let's see how this works on a computer here. Here we have the red wave is the incident wave coming in, and this end here is fixed. So this is the black is the shape of the string overall. So when it reaches the end here, it's going to reflect, and you're going to see the reflected wave is blue, and that's upside down compared to the red wave, or out of phase. And what happens, because the red and the blue are always out of phase from each other, you're always going to get destructive interference at the very end here. And so when you add those two together, you're going to get nothing. And this N doesn't stand for nothing. This N stands for a node. Wherever places, there's other places like here, you always get destructive interference because in this case, because of the wavelength of the wave is just right. And those are called nodes, where you always get destructive interference. The places in between the A's are called antinodes. That's where you always get constructive interference. Okay, so standing waves, there's actually a lot going on here. You have an incident wave, which is red, and a reflected wave, which is blue. And you get regions of constructive or destructive interference. And at the end here, too, this other end is fixed. There's a node at that end. And so the reflected wave is going to reflect again, and you're just going to keep getting reflections back and forth and back and forth. The frequencies or the waves that have the right wavelength or frequency will continue to add up, and the ones that will have the wrong frequencies will destructively interfere and will get killed off or die down. Now that we've seen how standing waves can be created, let's think about how to get the relationship between the wavelength and the length of the string for a certain size of a wave. So imagine we have our string here, and it has a total length of L, and we want to find the wavelength as a function of L. So we know that we have to have two nodes at a node at each end, and so the longest wavelength I can fit in here is if I just have no nodes in the center and I just have an antinode in the middle. The problem here is that I need to have a full wavelength, I need to have both a peak and a trough, and so I'm going to have to draw my extension of the wave out here. Of course, there's nothing out here, but to have a full wavelength, that I need to have double the length. So one wavelength is going to be two of the lengths here. This is called the first harmonic. And this is the main sound that you hear whenever you hear a guitar string or a stringed instrument played. Let's think about the next biggest wavelength that we can fit inside here. That satisfies the boundary condition, so we need to have 0 at the end, or nodes at the end. And here I had no nodes in the middle. Here I'm going to have one node in the middle. And I can draw a peak here and a trough here. And, well, this actually conveniently is exactly equal to a wavelength. So I'm going to call that, the wavelength is just the length of the string in this case. This is the second harmonic. Okay, let's draw one more and then we'll look for a pattern here. Okay, so we can draw our length of our string like this, and we have to have nodes at the ends because of the boundary conditions. Here I had 0 nodes, here I had 1 node in the middle. Here I'm going to have 2 nodes in the middle. I need to divide this up into 3 parts here. So I have 2 nodes in the middle. Okay, so then this will give me a peak here, trough here, and then another peak here. But in this case, one wavelength, I just need one crest and one trough. So this is actually one wavelength. And so let's see, you can think of this as being divided into 3 different parts. And I just need 2 of those parts to make a full wavelength. And so this is going to be 2/3 the length of the whole string will be one wavelength. Okay, and this is, of course, the third harmonic, and so on and so forth. Okay, so what I want to do is I want to find the wavelength of the nth harmonic. And so let's see if we see a pattern here. This is 2L. I want to write these as all as fractions. So this is 2 over 1 times the length. This is 2 over 3. I notice a pattern here. I have 2's. Let me put a 2 here. But this is really 1, so 2 over 2 is 1. So now that I have it like this, I think you can see the pattern. 2 over 1, 2 over 2, 2 over 3. This is going to be, the wavelength is going to be 2 over this first harmonic, second, third, so this is going to be n right here. Okay, so this is how you derive, using the boundary conditions, how you derive the relationship between the wavelength and the length of the string, or the length of the size of the object.